This is the section we'd like to devote to so-called lattice methods, which look similar to finite difference methods in the sense that you actually create a mesh of your underlying stock values S, and you compute the solution of your option price on the mesh in a certain way. Lattice methods are a bit different because they're older and maybe less flexible than the finite difference methods. Nonetheless, we would like to talk about it because you see the binomial method, for example, which is a special kind of lattice. You see it in books on pricing, options and interest rates. So we want to show you how to apply the binomial method to one factor and later on to two-factor binomial methods option pricing model. Since it's so ubiquitous, we want to do it and to show you actually how to set it up and how we've set up in C++ and how you can actually extend it and use it. And again, as in all the exercises, it's to gain programming experience in actually writing some option stuff. Basically it'll be a little option calculator, because if you're doing some other tests with other numerical methods, you'd like to have the binomial method as a second opinion. So you run the binomial method as well to see if you get the same answers. So it's a double check. One of the issues here we want to talk about is that the way we've done it is with flexibility in mind. So we want to design it so that you can actually extend it and reuse the code and the algorithms and so on. So you can probably write the binomial method, a very simple one, in 10 lines of code or something, but we want to extend it, so we need a number of classes and each class has its own responsibilities. Okay, so the background of the binomial method is it's a generalizable numerical method for option pricing, and it uses a discrete time lattice model. So you have a discrete points at which your stock is defined. So we want to describe the behavior of the stock as you go from the current time right up to the expiry time, big T. And it was useful for American options. So American option you can exercise at any time right up to the expiry date, and Bermudan options, which are like options which you can exercise at specific times leading up to the expiry date. The binomial method is easy to implement. It's a simple method. It's not the most accurate. It tends to oscillate sometimes depending on the number of time steps you choose. Nonetheless, it's a good example for when you're a student. So the input to the binomial method is the so-called, we need to describe the underlying stock, and there are two ways of doing it. It's mostly a stochastic differential equation in the so-called additive form or the multiplicative form. So basically the multiplicative form will be just in S, and the additive form you actually just change variables, and it makes this stochastic equation a bit easier. So when you're going up your, maybe I should go to a diagram in a moment. Let me go to the diagram here. You start off with here's the in the variables S, the stock price. At every point here's the value S. So let's assume it's got the value S at a certain time. A delta t time interval later, it can go up or down. That's the model, that's the approximation or the assumption. U is a number greater than 1 and D is a number less than 1. So at every time level it can go up or down. When we're in the change of variables, we have a delta t as well, but we also can go up plus delta x, and x, this should be minus delta x, right? It could be a negative number. Okay, and here's a basic mesh here with the three time divisions. So the number of time steps is 3 divisions. So go up or down. You see it's recombining, so the values down here, the values up here. Okay, so let me go back to my text. So we have to define the U and D parameters I've just shown you a moment ago, and there are different ways of doing it. Each researcher or practitioner has his own values, and depending on the values you get different answers. The two processes are as follows. The first process is called the forward induction. In other words, we go from time t equals 0, that's now, to time t equals big T, in which case we actually create the lattice of mesh points, so if you're underlying. Backwards induction going is from big T to 0, where we actually compute the price by going backwards. And as you navigate, you could have different conditions. So for example, when you're pricing backwards, you can check if the constraints are satisfied for numeric and option early exercise, or if you've hit a barrier, in which case your option price might be knocked out, be equal to 0, whatever. So there is a bit of flexibility in the method. So the again, the basic stochastic differential equation is, here's the change in the underlying. Mu is your drift factor, S is your stock price, here's the small delta t, which is the time change, sigma is the volatility, which is the sim constant, dw is a Wiener Brownian motion process. So this is my basic PDE or SDE. I have two values, up and down, and we need values for U and D because we need U and D to compute the mesh in the forward direction. We got the probability that an asset is goes up, so it's U times S, and the probability that it goes down is ds. So we need PU and PD. So it either goes up or down. So of course PU plus PD equals 1. So here's again my mesh. So we create my mesh in this way. The depending on the kind of scheme you're using, CRR is Cox-Ross-Rubinstein, I believe. Your up parameter is an exponential, so it's greater than 1. So you get the R minus half sigma squared delta t plus sigma square root of delta t, and the down is this quantity here. So if you work it out, the up, the probability of going up is a half, and the down probability is 1 minus the up probability, of course. So the J or Jarrah-Rudd, I believe, you got different values as well. You see the exponential is greater than 1, and 1 over the exponential, which is the exponential of minus sigma square root of delta t, is less than 1. So you got different quantities for your up and down probabilities again. So you will need each of these parameters. You will need the U and D for the forward induction phase to actually generate your stock mesh, and you need PU and PD for going backwards when you're actually computing your price. So basically, for an American option of going backwards, we're going backwards from we have a discrete mesh at level n plus 1 at the point j plus 1 and the point j. This is for an American option here with the factor, the constraint built in. But basically the term here, just let me draw it. The term here, this is my European price. So basically I have to compute this quantity going backwards from the expiry time t right down to t equals 0. K is my delta t, so the K here, which I just talked about a moment ago, this is delta t. This is your mesh size in the t direction. Of course, if you're using American options, you have to compute the European value and check against the constraint again. So that's just an extra option at your mesh point. Now, okay, so that's a bit of a binomial theory. Personally, I would say go off and study the binomial method in the book by Hull, for example, or as I've said, the book by Claylow and Strickland is an excellent book. It's an oldish kind of book, I suppose, but the methods are very good. It's got lots of examples, lots of motivation, and that's a good way to learn. That's not part of the course here. The part of the course is to actually take the model and the schemes and the algorithms and map it into C++. So there's a lot for you to do, but of course once you get into universities, for example, or you're working in business, you can do it yourself. So we want to design a so-called flexible binomial method. What do I mean flexible? Everything's flexible. Everything can be created and modified, almost. We want to learn how to produce the appropriate data structures and design patterns. What do we mean by the data structure? It's like a matrix here. First of all, the lattice here, it's like a vector of a vector, and that's the way we've actually implemented it in the code which I give you as well, which you need to study and work out. So it's a vector of a vector. So the outside vector has got 1 inside. Now it's got 2 inside. It's got 3 inside, 4 inside. So as you progress, if we had more mesh points, more subdivisions, you get bigger and bigger internal vectors here. So we need not just a homogeneous two-dimensional matrix, but like a lattice structure. So that's data structure first of all. We need also design patterns. We need to be able to change flexibly. So what do I need to change flexibly? If I got other methods besides CRR and JR, could be somebody else's method. I don't want to hard code the formulas here into my C++ design. I want to have some kind of flexibility so that I can actually change at runtime from one model to another. Now to this end, we're using UML. We talked a little bit about UML already. So basically let me go back to my pen. I got my binomial method, which actually is, let's say, the mediator or the boss, the manager of the whole system. It talks to its lattice. So the lattice is the data structure. So you need to create a lattice to generate the mesh points in your S direction, and you need the lattice when you're actually computing the price itself. And I call it here, it's got a pointer or a reference to a strategy here. Strategies can be for calculating up and down and the probability. You've got the CRR strategy. There should be JR strategy, so it's the Jarrah-Rudd strategy, and a modified CRR, etc., etc. I've got lots of examples. But whatever way you look at it, I can configure my application to use different kinds of binomial strategies. So your binomial method knows nothing about the actual implementations of these specific algorithms. All it knows is a base class here with the corresponding member functions, pure virtual member functions. So the classes for, as you will see in the code later on, when you look at the code and run it, we have so-called recombining lattices. So in other words, if I go back to my class here, it's quite a sophisticated class I've created, because not only does it work with binomial method, but it also works with trinomial method. So you can give the degree of your method up. You can say it's binomial, trinomial. It's recombining because if I look here, this goes up here, this guy goes down. So the up from this guy is the same as the down from this guy here. So these two neighbors each has a recombining line, as it were. So that's the first usefulness. We've got algorithms. It's a so-called strategy pattern to compute the ups and down jumps. These are just basically classes which implement a pure virtual member function in the base class. So the client only talks to the pure virtual member function. We've got a central mediator, which is the binomial method class we've told you about. So it does one thing properly. It talks to the lattice, it talks to the strategies, and it actually computes the price for you. Later on you'll see in the code I've got some factory objects for actually creating option data. So you can actually see, so in my main program, maybe like the way you've done it in MATLAB, you don't need to create the data in your main program. You have to create it, but you let a factory object create the objects for you, the data. Okay, so that was a very short introduction to the binomial method. The best thing would be to go into the code, run the projects, and do the exercises, and study the theory of the binomial method and the whole motivation. Because once you start studying it, you start studying the code on the disk I've given you on the course. You start to understand it more, and the exercises later on as well. So we'll take a break here, and I will see you later. Bye.